Uh, so we're going to start now. Well, in the beginning, okay. Well, first of all, I'd like to thank Dr. Malky for. Just a moment, I have to. Okay, well, first of all, I'd like to thank Dr. Malky for coming with us and share his experience with us this afternoon here. Well, I'll read a short resume of your for a moment. Well, Dr. Malky is Associate Dean for Academic Affairs in the College of Technology and Professor of Engineering Technology Department. Malky teaches undergraduate and graduate courses in engineering technology. He's a senior member of IEEE and was associate editor for IEEE transactions on fuzzy systems. He spent 2 summers at the NASA Ames Research Center as part of the ASEE NASA Fellowship Program to work on vibration control of UH-60 helicopters using neural networks in 2002 and 2003. His research interests are applications of neural networks, fuzzy logic controllers, and design of fuzzy logic controllers for industrial applications. In addition, his research includes modeling cyber attacks on smart grids using mathematical programming and reinforcement learning. He has been either PI or co-PI on several NSF grants and 2 Texas Workforce Commission projects. He received Fulbright International Education Administrative Program in France in 2016. He has published more than 75 refereed journal conferences, papers, and secured more than 4.6 million on external grants as PI and co-PI. So, Dr. Malky, thank you very much for coming. Please start your presentation. It'll be nice to listen to your talk.
Okay, good afternoon, everyone, and thank you for your introduction, and thank you for inviting us to participate in this conference, although remotely. I have been in Brazil, I guess in 2018. I attended the conference in Sao Paulo, and Brazil is a beautiful country, very advanced country, and I'd like to visit sometimes in future, but maybe after COVID, we could attend face-to-face conferences. And I'm not sure what you do right now in terms of the attending classes. Here in the US, in the spring semester, basically we turned everything to online. This fall, we had a majority of courses online. We called HighFlex, which you teach synchronously. There were some students face-to-face and remaining, I guess, online. And next spring, again, we will be majority online and we will have some face-to-face classes. I just wanted to mention how we work. I work from home. And first, I'd like to thank Dr. Edebalto Tesakra for inviting me for this conference. And I also like to acknowledge the organizing committee, as well as my master's student who is also attending this meeting right now. and his name is Ozuyama Ensaka. So this is his work. He presented his master's thesis just a month ago. And I proposed 2 topics. I think they picked this one. And I'd like to discuss his findings, and whatever credit or blame should go to him. Okay, as you can see, the topic of the talk is lithium-ion battery prognostic and health prediction using machine learning. So the outline of the talk is as follows. First, we talk about briefly about introduction and the battery prognostic and health prediction. Then we use NASA Ames battery prognostic data repository for validation of the proposed networks. And then we use various methods to compare battery prognostic and health prediction from data-driven models and traditional and advanced time series models and neural networks and deep learning models. And at the end, we show the comparison results and discussion, which will be compared as well. So am I going slow or fast?
That's great. It's okay.
Okay.
You can go on that way.
Okay, very good. So according to recent statistics provided by Grandview Research Inc., the global lithium-ion battery market is expected to grow at average annual rate of 17%, and it will reach to more than $93 billion by 2025. So it will be a huge market for the lithium battery market in the future. I'm sure probably it's the same in Brazil. The future of the car industry is shifting towards the electric vehicles. So obviously the battery is one of the important and hottest topic of research in everywhere. And batteries evolved from various modes. So originally they were they were not as efficient as the lithium-ion batteries. Before lithium-ion batteries, it was lithium had some safety issues, but so this battery prognostic and health prediction basically provides safe and efficient operation of battery management system, and it also provides accurate estimation of the remaining charge capacity and lifetime of battery. And we know that battery failure can lead to loss of power, downtime, and several and even severe accidents. So it's very important to have a efficient battery prognostic and also health prediction. This 2 figure shows physical battery measurements as well as data-driven model. The one on the left-hand side is just, equipment measuring the health of the battery. The one on the right-hand side is mainly data-driven model using softwares and so on and so forth. And as complicated electromagnetic characteristics becomes more complex and complex, we need to improve the battery prognostic and health prediction, especially using data-driven models. So what are the potential applications of this battery prognostic and health prediction? Obviously, there are many of them, but the most widely used one is the car system. because we know that the future of the cars will be electric vehicles or battery operated. So in order to have a better health management and the life cycle and health of the battery, we need to have a better prognostic of electrical vehicles. And so what are the prognostic and diagnostic models? There are three different models or methods. One of them is equivalent circuit model. The second one is physical-based model, and the third one is data-driven model. In electrical circuit models, as you can see, I'm sorry, I went too fast. So this is basically like an RLC or RC network. But the model represents the complex flow of ions, electrical charges, using an electrical circuit consisting of network of resistors and capacitors. Then the second one is more like physical-based model, which they consider mathematical representation of the battery and the physical and chemical reactions of the battery. And the third one, which is data models, basically they heavily depend on the data and experimental and operational data of a battery. And this leads to, let's say, data-driven models such as neural networks and deep learning and in general machine learning models. And whenever you do not have like a physical model or mathematical model, or in general you do not have a very good model, you could use data-driven models. And this picture shows how a prognostic and diagnostic framework of data-driven models. As you can see on the left-hand side, let's say you have a set of data and you do some type of data analytics to obtain the parameters for both testing and validation and training. So for training, basically you need to do pre-processing and also different batch generation for the training, and then you feed data for neural networks model and train it. And then after training, you have another set of data, which is called the validation. You do the same pre-processing, and then you test it and validate to obtain the optimized model. Once an optimized model is determined, then you use training data, to test the performance of the model. So this is very generic model for all, let's say, neural networks models. So now I like to define some of the terms that we use in the battery operation and diagnostic and prognostic. The first one is state of charge, which defines the relation between the existing capacity to the capacity of the battery when it is fully charged. So it's basically the ratio of the current status of the battery over full charge and multiplied by 100%, obviously. And the second one is the state of health, which basically expresses the relationship between capacity of the battery in fully charged state to the nominal capacity when it has never been used. And this one is also the ratio of the current over the nominal value. And the third one is end of life, which is called EOL, is the threshold value at which the actual capacity has decreased to 70 or to 80% of its nominal value. And then we have remaining useful life of the battery, which is defined as the total of complete charge and discharge cycles before the battery is below 70 to 80% of nominal value. I'm sure you all know that different batteries have different life cycles. They may range like for this particular research, there were about 160 cycles, but let's say for Tesla batteries, they go to more than thousands and like 8 years. And I have seen, like they say, they are trying to make sure that they could reach even in 1 million miles before you can replace them. So it's they are becoming much more efficient. And remaining life is basically the difference between the actual and predicted useful life of a battery. And then battery management system basically is managing a battery and ensuring that the battery is within the safe operating limits. In terms of setting the experiment for neural networks model or data-driven models, normally you need to have like sensor data where you obtain the data, and the next step is like you take the useful features that you want to use during training and testing, and you train the network, and then obviously you have to build a model and the parameters of the model and train it. And in terms of the data that, as I said before, used in this particular project, we use the data from NASA Ames, and the data set includes various parameters, as you can see, from the temperature, from voltage, current, and current ratio, and so on and so forth. But I believe he only used the voltage, current, and temperature for training his networks. And also, if you look at here, there are 4 different batteries. So it's not like B005, 6, 7, 8. These are basically identical batteries, but I'm sure the cycle time and the chemical within might be a little different once you use them. So in terms of the methods and the objectives of this research, the first one is identify the prognostic problem and evaluate the state of health of the system. And then in order to do that, you need to pre-process, normalize data, and build your data set for both training and validation and testing. And then next step is build the architecture and fine-tune the parameters of the model and test the results. Some of the main contributions of this research is as follows. One is we established a state of charge and training useful life of a battery using classical machine learning models, and then compared to single, multi-layer, and deep learning neural networks. And then he also used recurrent neural networks and extension of recurrent neural network, which is called echo state networks, to compare the performance of all of them on the same set of data and see which one performs better. Obviously, if you look at the research in this area, all of these are being used by various researchers. But the only one that his main contribution is he introduced echo state networks, which has not been used in the past. And from the results that we will show a little later, the echo state network performance is superior to other training models for this particular research. So, as I mentioned, the batteries are changing every year, and they are becoming more complex and more efficient. And in terms of the price, also their prices goes down significantly. And this shows like from 2010 through 2019, the price dropped from, let's say, 1,183 to 156. So this price drop and improvement in the batteries also creates more challenges in terms of computation and creating many partial differential equations for physical models. So because of that, one way to resolve this issue is use neural networks to capture the complex models of the batteries to improve the efficiency of the estimation of the health of the batteries. So some of the advantages of data-driven models are as follows. First one is, as I mentioned a little earlier, it eliminates the modeling of complex internal battery dynamics. Then they are computationally efficient, especially once you train them, the testing is a lot more efficient. And then you can use them in real time, especially when you are using them in real batteries. It's critical to have real-time prediction, and they have a high model accuracy. I'm not sure how much you see from this figure, but this figure captures all different neural networks models that published using machine learning. And basically the left-hand side shows different methods, and the right-hand side feature sets input, what type of features they use for training. And the last part is the output, which is either a state of charge or a state of health or remaining useful life. And then the last column is basically the error. So the error obviously ranges from, let's say, a minimum of 1 up to a maximum of 12, depending on which model you use. So for machine learning approaches, obviously they require a lot of data, and then because of the life cycles of batteries increase, so you can capture a lot more data, and then since machine learning approaches or neural networks models use a lot of data for training, so they become very useful in capturing a lot of data for machine learning approaches. If you recall, I said we compared traditional machine learning models and then recurrent networks. When you talk about traditional machine learning models, those are k-means algorithm, which is based on collection of training instance for the target vector. Given a new instance, they try to find the similarity using a distance metric. The second one is the support vector machine, or SVM, and they rely on a kernel function, and the objective is to find the function that deviates from the output to greater than an error at each training set. And the third model is linear regression algorithm, which is mainly a linear combination of input variables. And then we have the neural networks and deep learning models, which I'm sure you're all familiar with feed-forward neural networks. You have the input layer, hidden layers, and the output layers. And the next one is recurrent networks, where based on, in the previous case, in feed-forward, there is no feedback from the output of the neural network to the input. Whereas in this case, the output of the neural network is also fed back to the input. And in addition, you have the input as well as the memory for training the network. This is just one cell of this recurrent neural network, which is shown on the right-hand side. The next thing that you see these tables, basically they represent the parameters for training various models used in this study. So it is K nearest neighbor, SVM, artificial neural networks, and so on and so forth. And those are nothing but just various parameters that you have to use them for training purpose. Now I will talk about the results of state of health using various methods. And the first column shows the models, starting with K-nearest network and linear regression, SVM, and so on and so forth. So, and these are the batteries, obviously, 6, 7, and this should be 8. It's not 18, it should be 8. It's just a typo. And as you can see, different models have different, basically, results showing in this table. And basically, in this case, the deep neural network performs better than the remaining networks, and this is basically the error. So the next results is for remaining useful life of the battery, and here the table basically shows in the left-hand side, or the first column, is basically the error, which is mean percentage error, and also the RMS error as well. And the right-hand side, or the columns, are basically various network. And if you look at here, there are three, let's say, set of data. The first one, second one, and third one. The first one shows useful life prediction after the Fourier cycle. And if you look at, compare all of these, you can see that echo state network performs better than the remaining of those. And as I said, this is just nothing but the various errors that you see in these models. And the second set of data in this table is training the network with, at 80th cycle. And you can see that they improve a little bit. And finally, with 120th cycle, the performance of the networks improves compared to 80th as well as the 40th cycle. And the next table shows the remaining useful life of prediction results for all these models. And again, these are the models from K nearest neighbor up to echo state network. And again, we used first the 40th cycle, and then 80th cycle, and 120 cycle. And the first row is the actual end of the life cycle. The second one is the predicted one. And the last one is the cycle error. So as you can see at the Fourier, obviously there are some errors for some of these algorithms, and it varies from, let's say, 14 to lowest one with echo state network, which is 2. And as you increase the cycle time in the data, so the error also goes down for most of them. And at 120th, you see that the error is almost 0 for most of them. except like RNN and DNN, which is 1 and 3 respectively. And finally, the conclusions. I think I'm almost on time. So in this work, we established state-of-art charge and remaining useful life of a battery using classical machine learning models and also recurrent neural networks and long short-term memory. And based on the results, the proposed eco-state network model is able to eliminate modeling battery dynamics. It increases computation. Computation and efficiency of the life of the battery, and also achieve real-time prediction, and also high model accuracies observed from this model. I think that is the end of my presentation. If you have any questions, we are more than happy to answer your questions.
Thank you very much, Professor Malki. Yes, it was very nice to listen to this presentation, because, you know, I've been working in this area of neural networks for more than 30 years.
Yes.
And I'm very glad to know that what we are doing here, we are also in the right direction. So you see how important is this to have the information of what are you guys doing there in the United States, and especially in Houston University. I'm very happy for that. I've seen you are using, you made many choices on many architectures of neural networks. And what is interesting in this case is that you have decided and found one of them which would be the best. And one question I would like you to ask me is, are you intending to implement those neural networks, for instance, in a car, and decided by the use of the neural network to make this kind of prediction?
Ultimately, that is the goal, but I think it's up to the car manufacturers, let's say, to use these. I'm sure they are using some type of machine learning algorithms. I'm not sure how much of that is being used in Tesla. The good thing about Tesla, what I have heard, that they share their whole, let's say, building models, the battery operation with whoever wants to use it. What I have heard, that since they build everything from the scratch in their manufacturing, so everything that they build is unique in a way. They don't copy from other, let's say, manufacturers or materials or batteries. So that's what even I was wondering why they even share their, let's say, algorithms and batteries and operation with others. But since others basically copy from them, they will never reach Tesla. So back to your question, I think it's up to us. We propose these ideas and write proposal for car manufacturer to see if they will fund us to do further research in use of neural networks or machine learning in general for battery prognostic.
Okay. Yes, because one thing that's interesting is that in the past, it would be impossible to use neural network for this application. But now with the computational capacity of microprocessors,
Right.
that's obvious that it's possible to have that inside the car and doing this prognosis. That would be very important for car manufacturers.
Right. I'm sure you know that if you look at the history of neural networks, I'm sure you teach that. I mean, it goes back to 1940s and all of that. The resurgence became in, let's say, 80s after introduction of, let's say, multi-layer neural networks and backpropagation training algorithms. And then it reached to a steady state, let's say, towards end of 90s. But you look at this second wave of resurgence in lately because of all these deep learning models. And you can see that actually, especially in robotics area, they are widely being used. So nowadays, artificial intelligence, machine learning, and deep neural networks are becoming much more popular than previous years. So there's a lot to do with the neural networks right now.
Yeah.
Obviously, as you mentioned, with the power of microprocessor and the computational power of computers, it is a lot more easier to actually implement them in real time.
Yeah. Yes, so nice. Well, if there is somebody that wants to have any question, I'll be glad to translate to Dr. Malki. So I'd like to thank also Mr. Nsaka for coming with us and joining this presentation. Thank you very much for staying here.
Yeah, can I ask him to give like a minute talk or so? Because actually, I understand that he work on these in industry. Maybe he could say a little bit more.
Oh, that's nice. I
Yeah,
would be glad to hear from here.
yeah. Ozyama, do you want to say a few things about what you did in industry?
Yes. Thank you so much, LD Beto and Dr. Maki, for this opportunity. We have worked on this research for over a year, and one of the motivations and which Dr. Maki really supported this project is because I've worked for an industry that really relies on lithium battery for their operation, and it's called the Halliburton Energy Services. They handle most of the world's oil reserve in terms of they find the hydrocarbon underneath the ground, and they use drilling tools that are able to, they are called formation evaluation tools. So they are able to go underneath the ground and actually evaluate the hydrocarbons in the ground and make a decision for an exploration company like ExxonMobil or Chevron and say, hey, we do not think the hydrocarbons in this ground is profitable enough to invest further. So they actually are the eyes of drilling exploration. And so it's a very critical component. And when I worked there, the failures we had that were the most expensive were battery failures. And so each of these drilling tools use lithium batteries. And when, for instance, in one of the cases, we had actually gone down 30,000 feet and we were drilling through when all the signals died and they couldn't continue because it was a directional drilling, meaning a drilling that goes at an angle underneath the ground. So, and if there are side wells, it might lead to collision and explosion. And one of the main reasons we drill with directional tools is to have the anti-collision. We keep a safe distance from an existing oil field underneath the ground. And so what happened when they pulled out 30 feet, it took hours, over 24 to 48 hours to get the tools back up, replace the battery, and then go back down. And so an hour on that rig that belonged to Shell was $1.2 million. So they lost.
Oziama, what methods did they use? Did they use any machine learning algorithm?
No, there was no machine learning in that drilling tool. All we did was, I think in Dr. Markey's slide on page 2, you see one on the left that has a multimeter. We just measured the capacity, the current, before sending the tool. So basically what we did was we did an evaluation and sent it. So when it went down, we didn't have a way to tell if the battery was good. So if we had a system like this, while drilling into the hole, maybe 5,000 feet in, we see the capacity drops. And then we tell them, hey, we think we need to pull back up and replace this battery. There is something weird with the battery manufacturing. But because they didn't have that, they kept going. And then when the battery died, it was an instant failure. And this thing just happened once, it happened several times. So millions of dollars has been lost. So this project, this research is actually very critical for oil and gas companies. They will be excited to have this as a real-time element in their drilling process. And I know the whole world is moving away from oil and gas, but that's just to show you one critical application. Since I was actually involved, I learned through being from a maintenance electrical engineer, measuring those batteries myself. There are times we load test the battery and they are completely dead. So that experience translates to the need for this system in oil and gas, and also like reading through NASA's, the reason NASA is very interested in this is that they send space satellite system cubes to space and they all contain lithium batteries. And they need a way to monitor from Earth, those batteries are good. And if they are not good, they have a system to replace those batteries. And so they are also trying to utilize these models in their systems.
Oziama, I think you added very good points. I think we have reached like 45 minutes.
Okay, thank you.
Thank you so much. You added very useful information.
Yeah.
Thank you.
Yeah.
So I guess if you don't have any questions, I wish you all the best and hope that we come to Brazil one day for face-to-face conference in the future.
Oh, thank you very much. Thank you, both of you. And I'm sure this research is very, very important. As Mr. Masaka said, there are many, many applications for NASA, for oil companies, and so on. So, and we will find thousands of applications everywhere. Well, thank you very much. Thank you for sharing your time with us.
It was our pleasure and honor to participate in your conference. Thank you.
Oh, thank you very much. Bye-bye. Have a nice time.
Yeah.
Eu queria pedir para o pessoal que fiquem aí na conferência, que nós vamos ter o encerramento com o professor Finzer, vai fazer o encerramento da nossa conferência, ok?
Aqui.
Ok, professor Finzer, já terminamos de fazer o encerramento da...
Já posso falar?
Já abri.
Já posso falar?
Já.
Posso falar?
Já apareceu. Peraí. Isso.
Ali, tá certo?
Isso. Professor Física, pode falar. O Edilson te chamou. O Edilson te chamou, pode falar. Pode falar.
Posso falar? Boa tarde a todos. Permitam-me apresentar-me, José Roberto Fizer. Sou coordenador do curso de mestrado profissional em Engenharia Química. Com grande satisfação, tenho a honra de representar o reitor da Uniub, professor Dr. Marcelo Palmério, e o pró-reitor de pesquisa e pós-graduação e extensão, professor Dr. André Luiz Teixeira Fernandes, no encerramento do quarto, então, EDEPA. Esse é um momento de agradecimento a inúmeras pessoas que participaram dos preparativos. Como sempre, pode-se esquecer alguns, e então vou representar todos em algumas pessoas. O grande presidente do evento, professor Dr. Adriano Davidson de Lima, professor Dr. Leonardo Campos de Assis, coordena comigo o programa de pós-graduação. Rayane dos Santos Silva, da comissão de apoio. Professor Dr. Edilberto Pereira Teixeira, que foi charmem de palestras de expressão dos nossos convidados estrangeiros. Professor Marcelo Costa Dias, que participou da comissão de evento. Marco Antônio Gonçalves, da CBMM, que teve uma participação muito grande na participação deste evento. A equipe do IQBEL, pela tradução das conferências, na pessoa da sua diretora Janaína. O nosso muito obrigado. Temos que agradecer todos os docentes do programa de pós-graduação em Engenharia Química e corpo docente, não deixando de citar a equipe de tecnologia de informações pelo apoio expressivo e também diversos outros profissionais da Uniub. Agradecimentos expressivos ao Conselho Regional de Química, na pessoa do seu presidente, Dr. Wagner Pedersoli, representado pelo professor Euclides de Lima. Agradecimentos à CBMM, Companhia Brasileira de Metais e Metalurgia, na pessoa do mestrando Marco Antônio Gonçalves. O IFTM, professora doutora Carolina Rodrigues da Fonseca. O FTM, professor doutor Deusmac Carneiro Ferreira. Por favor, outras pessoas que participaram muito nesse evento, sintam-se representados. O EDEPA tem uma função de catalisador, juntando ciência, tecnologia e engenharia, envolvendo profissionais de diversas áreas para que pesquisas futuras em processos agroindustriais sejam úteis à sociedade. Imaginamos que cumprimos a missão. Muitos trabalhos de diversas universidades e instituições de pesquisas foram apresentados nestes 2 dias. A comissão organizadora entende que, mesmo em período de pandemia, o evento foi um sucesso. Nessa edição, tivemos as conferências de pesquisadores do exterior. Vou citar os 4. Dr. Yashiro Arada, da Toshiba, Dr. Robson Monteiro, da CBMM, Dr. Kenneth Loparo, do Instituto ISS-ACS, e Dr. Heidar Malki, da Universidade de Houston. Quero enunciar a todos que já se definiu a data do 5º EDEPA, 10 e 11 de dezembro de 2021. Já convidamos a todos para participarem. Como o EDEPA relaciona-se com a disseminação do conhecimento, finalizo com a frase célebre de Leonardo da Vinci: aprender é a única coisa de que a mente nunca se cansa, nunca tem medo e nunca se arrepende. Muito obrigado a todos. Fica encerrado nesse momento a 4ª edição do EDEPA. Não sei se era isso.
Podemos.
Encerrado. Obrigado, Edil. Obrigado, Larissa, pelo apoio. Obrigado, Robson.